All right. Now we're into our unit on energy. This video, we're going to go over some definitions and a couple of different laws with some examples. So hang in there. So energy is defined as our ability to do work. All right. Now, these are kind of physics terms, so you might be like, well, what's work? Funny you should ask. So work is when we take a force and apply it over a distance. All right. So mathematically, it's force times distance. You have to take that force and you have to push or pull something over a certain amount, like I said, of distance. If you sit and push something and you exert yourself, but it's not moving, no work has been done. Have a couple different types of energy: kinetic and potential. So kinetic energy is the energy of movement. All right, things in motion. All right, we have these awesome boats. They're moving really fast on the water. So they're moving. They have kinetic energy. All right, I'm sitting here on the couch. I don't have a lot of kinetic energy. Maybe I have potential energy, but anyway, things that are considered potential energy, anything that's not kinetic, that happens to be energy, sure. But we tend to think of stored energy, all right? So what's important in the world of biology is we're interested in the potential energy that are in chemical bonds, all right? If you're into physics, you might be looking at that roller coaster. It's at the top of that peak there, so it has a lot of potential energy, and then as gravity pulls on it, that potential energy is going to get converted into kinetic. This leads us to the first law of thermodynamics. All right, these are laws. The first and second law, they deal with energy. Okay, so the first law states that energy of the universe is constant. All right, so we can't add or subtract the amount of energy that we have out there. But it can be transferred, meaning to move from one place to another, or transformed, meaning to change from one type to another. Okay, so in this little picture here, somebody struck a match, lit it on fire, so that the potential energy that was in the match got transformed into kinetic energy and heat energy. So heat would be like a type of kinetic energy. And then the energy that the heat is going to get transferred from the match into the surrounding air. Here's an example with a nuclear power plant. So inside here we have the core of the reactor. All right, so it has uranium fuel rods, and those fuel rods have what kind of like the energy of the nucleus or nuclear energy. All right, so it's just sitting there, and then it gets spontaneously transformed into electromagnetic energy. All right, so that since the nuclei are a little unstable, they release X-rays or gamma rays, and then that gets transferred into the water surrounding it, and then that heats it up. So it went from nuclear to electromagnetic to heat. All right, so went in the nuclear, and then this pipe where we've got some water that gets heated up. Then that heat turns the water into steam, and then it goes to a turbine. So think of like a jet engines or something like that. That steam gets spun by the turbine gets spun by the steam. So the heat energy is going to get turned into mechanical energy, or the movement of large objects. That turbine uses mechanical energy. It spins like a magnet, or it spins a coil in a magnetic field, and then that turns mechanical energy into electrical energy. Then that electrical energy can go to your house and then get turned back into heat energy, like with a toaster, or light energy, like if you turn on the lights, like electromagnetic again, and so on. So that's transformation right there. I just went through a handful of them, right? So we went from nuclear to electromagnetic to heat to mechanical to electrical. So that's 4. This is a an oops, because that original reactor that you saw on the other page was Chernobyl, and this is just a kind of a grim reminder what happens when we don't take our first law of thermodynamics very seriously, or we make various errors. I'm sure now that it's much more popularized with HBO, you probably know some of the effects of kind of potential effects of nuclear power. Let's go on to the transference of energy. Here we have a refrigerator. All right, and I'll tell you first of all, most of your like kitchen appliances are usually you're heating something up. All right, or you got your stove. You heat up a pan, so you're going from the burner to the pan to the food. That energy is being transferred along the way. Same with a toaster and whatever else. Here's a refrigerator, and refrigerators are kind of interesting because what we don't do is there's no such thing as cold energy, so we're not taking cold energy and we're putting it into the refrigerator. What we're actually doing is we're taking heat energy and we're removing it from the refrigerator and from the freezer. Okay, and if you've ever felt the coils on the back of the refrigerator, you'll feel that they're warm or hot, and that's because that heat from inside the refrigerator is leaving. So that's a different type of transference, and then the lack of heat or the diminished heat that's inside of the refrigerator reduces the temperature inside. Well, we also have the second law of thermodynamics. And this one states that entropy of the universe is constantly increasing. This might seem like it's at odds with the first law, where it's saying energy is increasing. But no, this is entropy. This is disorder, okay? So as we do our transferences and transformations, what we end up doing is we end up creating more and more disorder. And that's very difficult because, as you know, one of the traits of living systems is that they're highly organized. And as a living thing, we don't like this whole idea that entropy is constantly increasing, because that means we're at odds with entropy. It means we need to do our best to try to stay as organized as possible. So it's a vicious cycle. We've got our kinetic energy, we convert it to potential energy, we create entropy. Oh, we're taking our potential energy, we're turning into kinetic energy. Oh, we create more entropy. It just goes on and on and on and on.